Continue from previous video where we calculate the I effective at the midspan, where we look at the I effective at the midspan. Now we're going to look at the I effective at the supports. Now I effective at the supports can be calculated by using the same equations that are shown here. I effective is equal to I crack in these brackets, that is given on page number 129 in the standards. Now in this equation there are four parameters: I crack, I gross, cracking moments, and the maximum moment at the supports. Now gross moment of inertia I was calculated previously. I can show it to you here. That I value was calculated was 2 times 10 raised to minus power 10. That was calculated here, 2 times 10 raised to power 10 millimeter to power 4. So that was calculated for the uncracked sections. Now cracking moment of inertia at the supports, that also we have calculated in the previous video. I can show it to you here with the cracking moment of inertia at the support. That I crack was calculated 10.46 times 10 raised to 9, that I extracted from the previous video. So ICR at the supports. So please note we are working this I effective at the supports. If I show it that one on the questions here, that we calculated the moment of inertia I effective at the midspans. Now we are calculating I effective at the supports. Now, and we have all the informations that we're going to use it at the supports. Now the moment, maximum bending moment at the sections, please note we need to use short term sensitivity load. So the equations that we can calculate was ml square over 8. Please remember that in the previous video we use where we calculate this WL square over 16, I think. Now this is structure analysis that we are taking this value, which is WL square over 8. Now W 88. I think in our previous video we checked that short term serviceability was taken 88 kilonewton per meters, that I substitute here. Now the length of the cross sections given in the questions, length of the span is given in the question, which is 9 square, and then divide by 8, give me the moment 891 kilonewton per meter. Now the cracking moments, that is given here, which is given in these equations here, which is Z, and that standard equations that also we done this one in the previous video. So I'm not repeating this P, AG and PE, where we have these force in the tendons for the stress, pre-stress. We are taking this 0, P times E is 0. Now we have these four variables, I over YT, FCTF minus sigma CS. Now in the previous video I need to have some correction also. I think I remember that in the previous video we make some mistakes here, which I like to correct it. Please note here in the previous video we have PCW. Now this PCW is the wave reinforcement ratio for compression reinforcement, and if you check our at the midspan, the cross sections, at the midspan, at the cross sections, we don't have any compression reinforcement, because if you have at midspans we have a negative positive moment regions. In that positive moment we have only tensile reinforcement, so we need to calculate only the tensile reinforcement, not the compression reinforcement. So I substitute this 0. That was not having big effect, but I think if you can correct this one in your I will leave the page here. It was had a small corrections that happening on this previous video, which is 70 kilonewton meters. So that is the small corrections that if you can note it for your previous video. Now here we follow exactly the same thing. These equations is your maximum shrinkage tensile stress given here. I copy this equation here. In these equations we are working on this side. Now at the supports we have a negative moment region and the cross sections given here. Now in these cross sections in the wave we have a compression reinforcement. As you can see, this is the this becomes you can see the tensile reinforcement given here when your cross section is here. At the supports your tensions or your tension is on the top, so you have tensile reinforcement here. So in the wave you don't have any tensile reinforcement, and please check the definition of PW. It says that wave reinforcement ratio of tensile reinforcement. In the wave we don't have any tensile reinforcement, so in this case we will take PW equal to 0. Now PCW, which is definition is given here, which is wave reinforcement ratio for compressive reinforcement. So we have wave reinforcement at the compression side on the wave. So we have this 1860 divided by thousands BW times D. Please note this D. Now this D, in the last video we are measuring from, D was measuring from this end to this end, but now this is reverse, so we need to measure from tensile to this edge, which this tensile to this edge. In the previous video we are measuring the D from tensile reinforcement to this one, so we have 800 take away 60, but in this case we will have, I think, same value, which is 800 take away 60. That will give me say 140 value, so that is 2.51 times 10 raised to minus 3. Now once you calculate these, all the parameters that you needed, we can use again these equations that is given in the standards, and we substitute this PW0 that I just explained in my previous steps, where we take the PW equal to 0. PCW we just calculated, that is the compression reinforcement ratio, and 1 plus this PW0. This is the Young modulus of the steels, which is given in the questions. If you go all the way to the start of the examples, you will see that Young modulus of the steel 200,000, and the shrinkage strain is given 800 times 10 raised to minus 6, will give me this 0 minus something, that will give you the minus value. Now if I use this MCRT, which is the cracking moments, that IYT, these are P equal to 0, that is the pre-stress force in tendons, and this P equal to 0, so these whole terms get 0, so the equations become these in the brackets. Now gross moment of inertia, 2 times 10 raised to power 10. I think we calculate this gross moment of inertia. It also called the moment of inertia of uncracked section was 2 times 10 raised to power 10. YT, please note this YT again. In the last one we used the YT value. In the last video we used this YT value, I think from this centroid one. From this tension surface to the centroid was 488, but now in this region we have tension surface at the top, so we have a tension surface here, so we need to take 800 take away 488, it gives me value 312. So please note this is the distance YT now in this section, so this will found by 800 take away 488 will give me this YT, which is substituted here 312. 3.4, I think we calculate these FCTF values in our previous video, that is applied here as well, because it will not going to change, but I can show it to you here, that FCF which is the characteristic flexure tensile strength, we calculated 3.4 megapascals. We just calculate these maximum shrinkage tensile stress, substitute here, this give me these numbers, divided by 1000 to get it in the kilonewton meters. Now we have all the required parameters to calculate I effective at the support, I crack at the support, I crack at the support. This I will not change. This I value is a gross at supports or at the midspan is same. Cracking moment at the supports and the moments at the support. So cracking moment at the supports, I think we calculated that one. I can show it to you again here. That cracking moment at the support, we had calculated this 10.46 times 10 raised to minus 9. This 1 take away 10.46 times 10 raised to 9, and that is the gross moment of inertia. I think I can show it to you again. I think we are repeating the same things again and again, but that will help you to understand the concept, which was we calculated 2 times 10 raised to minus 10 times 64, that we just calculated here, 64 over 891. I think in this video we calculated the moment, that was 891 at the supports, 891 kilonewton meter square. It gives me these numbers here. Now we need to do the quick check here, that its value should be I effective less than max. So for that we need to calculate AST over BD. If it is greater than 0.05, that will be I. If it is less than 0.05, we take 0.6 I. So in that case you can have AST 5600. Where is the AST coming from? If you take the tensile reinforcement in this cross section, AST was 5600 over BD was 1000, that's 1000, and D is the distance from the tensile reinforcement to the other side, which is 800 take away 60 will give me 740. It's give me 0.008. So I think 0.008 is greater than 0.005. So we are in this condition satisfied. So I effective equal to I. That is the gross moment of inertia, which is 2 times 10 raised to minus 5, and I effective that we just saw 1.05 times 10 raised to 10 is less than the maximum 2 times 10 raised to minus 5 millimeter power 4. So that is okay in our case. Thank you very much.